Welcome, everybody, and we have our preferred guest here, Dr. Sebastian Lobo-Guerrero. Dr. Sebastian, we already recorded with Dr. Sebastian a couple of records, couple of videos, and they were very successful and had lots of views, and people were very happy to have a lot of information and wonderful explanations about slope stability and board piles. Today, we decided to go through micropiles. And of course, Sebastian has also distinguished experience about design and construction of micropiles. He's a senior geotechnical project manager in a company well established, and they do consultation in geotechnical and other stuff. The name of the company is Aegis Incorporated, and it is in Pittsburgh, Pennsylvania, I think. So welcome, Sebastian. I'm very glad to have you again. Thank you for coming, and thank you for participating with me in this beautiful sharing of knowledge. Thank you.
No, thank you, Ahmed. Thanks for the invitation. It's been great the previous times, and I deeply enjoy our conversations. So looking forward to keep expanding, right? We started with slope stability.
We'll continue as long as you have time for me.
Absolutely. Always. So yes. All right. So yeah. I'm ready.
You can start if you want.
All right. So yes. So let me
anxious to see what you have today.
Thanks for the introduction. Just a quick bio there. I mean, you already kind of say where I work and all that, but I always like to expand a little bit, just where I come from and all that. I'm originally from Colombia, South America, so that explains the accent and the fastest speed of talking, because I grew up with a lot of Colombian coffee.
A lot of energy.
Yes. From the legal product of Colombia, not the illegal product from Colombia. We are not going to talk about the illegal product of Colombia. So, but anyway, I've been in the States for now 22 years. I came and did my master's and Ph.D. at the University of Pittsburgh. I started working in consulting, working at Aegis Inc. for a while now. And then I also came back to the university. So I currently am also an adjunct professor there, and I teach on the graduate program of Geotech, and I basically teach on all these topics that we have been covering. So today we have a special one, which is micropiles. And this is a very special topic for me, because it's something that I feel I have been present in my experience. I kind of saw the development of micropiles and how they became popular and how they became a standard. So, the first time that I hear about a micropile was 1999. I have the luck to go to the first job site in Colombia that have micropiles as foundation for a building. And it was literally the first micropile done in Colombia. So it was really good. And then when I came to the States, I kind of continued following the technology, study the manuals from Federal Highway Administration and all that. And eventually when I start working, I start actually applying them. So the outline for today, it's kind of simple, and obviously we're going to do it all as a conversation. But initially we're going to talk about what is a micropile, what defines a micropile, what types of micropiles exist, right? What are the components and the design principles? Micropile itself, the definition changes geographically and depending on markets. So we'll talk about that. Then we're going to talk about the construction sequence, how how do you construct them step by step, how you test them. It's one of the advantages of this technology. And we'll go through applications and examples, but really we'll go through those applications and examples through the conversation. It's not at the end, it's really just everywhere. So, let's start with a micropile. What is a micropile? And I'm sure we're going to spend some time here, because it's not a simple definition. So micropiles in its concept, it's in origin. If you go back to the Federal Highway Administration circular, the history of the micropiles really starts in the mid, like almost half century or 60s from the last century that we have. And it's a guy in Italy. His last name is Lisi. Lisi is the first one that comes with the concept of a micropile. And basically his original intention, or what he was calling a micropile, which is very different from what we do today, was that you are going to do some kind of, perforation in the ground, and you're going to do it better with inclinations, never vertical, always better. And what he wanted to do was to do some injections. We see it more like his definition. It's more probably what we call now.
He didn't
program.
like to make vertical, or you can't make a micropile vertical.
Correct. No. So initially he was doing
he was doing them incline. Yeah.
Incline, because what he wanted to do was a reinforced mass. What he wanted to do was not individual elements. He wanted just to go and start drilling, in all kind of directions, injecting grout, and making like a rigid body out of that, right? That's what I'm saying. Like today, that definition is more like if you're doing ground improvement rather than micropiles, because for us, micropiles now are foundation elements. Each individual is an element, right? So that was his initial definition, and he started using a smaller diameter. So it was a smaller diameter compared to what at that time was being used for like a small pile, like a small shaft. That's where everything started as a micropile. That's where the micro comes into play. Now, that technology evolved. It arrived to the US. Federal Highway was literally the first entity that started doing research on micropiles and trying to put some kind of design guidelines and some kind of design consensus. The way that they define it was, you have probably an element that is pre-drill, right? It has to be pre-drill. It's about 7 inches, 7, 9 inches, 10 inches, around that size. And you are drilling, right? And as you drill, you're going to have a casing. So the casing is basically, like a steel. I mean, we talked on drill shafts last time, but it's basically like a steel cylinder, a pipe that you advance as you are going down, as you are drilling, right? And that avoids that the soil collapses, right? Now, when you get to certain depth that you have a competent strata, in the original way that micropiles were done, you used to stop the casing, right? And then your drill bit used to continue after that, because the material is supposed to be competent. So it could be in rock, it could be in a very hard residual soil, something like that. Now, the beauty of the micropile since the beginning is that when you stop the casing, right, whatever is below is what is called the bond zone. Bond because you have direct contact between grout and that. But anyway, once you perforate all these, then you put a central bar. I mean, you take your drilling tool out, you put a central bar, and then you tremi-grout it with some kind of grout that when it hardened, then you end up having a pile. So it's basically the main concept is you have casing, then you have a central bar, and then you have grout, right? And that was really the element. Now, since the beginning, micropiles, similar to Lizzie's idea, are better. And the reason that are better is because they take lateral loads. So they take lateral loads in compression or tension in the axial direction. So if I butter and I have resistance on the axial direction, my horizontal resistance is literally, the projection of that axial force. So if I know the force and I multiply by the sine of the angle, that gives me my projection in the horizontal
plane. Basically, you don't want to use micropiles to resist lateral load.
Well, they resist lateral loads, but in axial component, not in bending.
Basically, their main force is axial.
It's axial.
And because if you want to use them to resist lateral load, so you need to incline them.
Exactly. So then the moment that you
incline so that they have a lateral component.
Exactly. You have a lateral component and then you have a vertical component. Exactly. But you are completely correct. They are never designed to take lateral loads on bending, like as a PY core, like you should never model it as a PY because the element is not stiff enough. You know what I'm saying? It doesn't have enough reinforcement for that. So that is kind of the concept. Now, the beauty of micropiles and the way they started really where they found, when they started and deviated from leases, where they found a niche was on retrofitting foundations. Because, it was the times that a lot of structures all over the world were being retrofitted because of seismic demands. So the beauty of micropiles is that you can go on an existing pile cap, you do it, and we're going to see pictures of the equipment that is utilized and all that. But it's easy accessible, a small diameter drilling, and then you can go and put the small piles, right, that now can take load. Now, another main advantage is that because you are working on bond, you are not working on embering, it's just bond, side friction. You can work on tension or you can work on compression. A micropile doesn't really care because it's just frictional resistance. So the load can go up and the load can go down. It doesn't matter. And that's what it makes it attractive at the beginning. The typical diameters are about 7 inches to 9.5. Those are like in the US, the main things. Things can vary. These are just like, typical values. And the bond length, and this is where differences start happening very quickly. The bond length for example, in Pennsylvania, where I'm located, right? If you are designing for transportation, for DOT, right? They specify that a micropile has to have their bond length, the resistance in bedrock. They do not accept any kind of bond length, any kind of resistance that is not on bedrock. When you look AASHTO, like let's say version 9 of AASHTO LRFD design, they give you tables for using it on soil, right? Especially if you use like pressure grouting. So depending on the market that you are, you may use it on bedrock, on soil, or it may be confined to bedrock. Around the world, I would say in my experience is that around the world, it's widely accepted to have micropiles in soil, as long as it's a
Yes,
competent
that's
structure.
true.
So I think transportation in the US in certain states is just a little more stringent.
More conservative.
More conservative.
In fact, it makes sense that a designer should not go to the solution by a micropile if you have lateral loads.
Correct,
or you should just make them inclined, so you can have always pairs.
Exactly.
One with positive angle and one with negative angle. So always you have the capacity to resist lateral loads.
Correct.
In fact, I have seen, Sebastian, I have seen less than 7 inches micropiles.
Oh, no, they are 6 inches, 5 inches.
6 inches I have seen, 6.
Yes.
I don't know if there is 5, but I have seen 6 inches.
I have seen 5 in very small loads in private sector, right?
Maybe
like in private construction.
Small houses or small
Yes,
structures.
correct. But it's more, Now, the other part that we were mentioning at the beginning, for example, the casing. Like if you take AASHTO requires the casing, right, as transportation. But in many countries in the world, the casing, they don't put it permanently. They just take it out after they drill.
Take it out, yeah.
So, again, it's just different practices.
Local practice,
experience,
local authorities.
Exactly.
We should follow, and engineers should understand that in every area there may be different regulations.
Correct. So so the picture that you see on the left it's a job that we did in Pittsburgh downtown. It's a bridge, and we have the micropiles. We have vertical and batter. Batter are because we're basically taking lateral loads, and what you see there that we're gonna talk later in more detail is one of the tests. It's a tension test, and the reason that I climb is because that is the one that I have put the highest load in my career, and I was so excited to see that the micropile took it that I climbed the frame and took that picture as acceleration. I mean, we put 500, a little more than 500 kips on that, which is 250 tons, which is a very high value for something that is called micro, right? I mean, you're talking those values in tension. I mean, that's a massive element. So to me, it's also full circle of saying, look how far we have come, that in reality, a micropile, it's almost like a mini drill shaft of big diameter, and you start crossing technologies, because then what makes it a micropile? It's just a name, it's just because it's called micropile and you have to follow a procedure, or what it makes it. But anyway, that was a great day, and that's the reason we took that picture. Now going into the design
I like the safety provisions. How you have a handrail, and these things are important in testing, because some people will get injured, or the shaft sometimes, the jack sometimes fly from its position if it's not connected in a good way. So people should be careful about these things.
And as a disclaimer, I climbed there, but only after we removed the load, right? So the testing was done, we removed the load, and then I climbed. You should never climb there while the load is there, right?
You are a coward in this one.
Yes. No, I mean, because imagine putting 250 tons on that thing, and if it fails, right, it's just gonna fly in the air, as you say. So
I usually put steel angles around. So Even if the jack moves or flies, it will
stuck.
hit the angles and keeps
that's actually a good
place.
that's actually a good advice.
It's good to think about safety.
Oh, absolutely.
Always. Some
Absolutely.
people they have their courage, or they think it's courage, they think it's self-confidence or whatever, but they do things, then they will when they have the problem, they will really regret that they did not think about the safety correctly.
Yes. No, I mean, safety is it's a way of thinking, right? It's like it's
in every step you should think of safety. In every step, in design, in construction, in testing, in quality control, in measurements, everything you should always keep the safety in mind.
Yes, absolutely.
This is where the doctor, this one?
This picture was in Pittsburgh. It was a bridge in Pittsburgh in the middle of downtown.
Okay.
Yes.
Okay.
Yes.
Okay, thank you.
Yes, no problem. So moving into the design manual. So this is basically what we have today. Really, really the main comprehensive manual is the Micropile Design and Construction, put together by FHWA. There are multiple editions of that, but it really started around the end of the 90s, and it became kind of like the main reference. Then after that, AASHTO obviously end up incorporating Micropiles. Typically the way is that FHWA, it's in the US, is the entity doing the research. They put the conclusions, they put the document, but AASHTO is really what becomes a code, and it becomes a law, right? Like you have to follow this if you're in transportation. So AASHTO incorporated Micropiles in section 10, which is foundations. And then the equations and stuff that we're going to talk today, they are all on AASHTO. And then different states take AASHTO, different DOTs, and modify things depending on their state. So for example, I have the design manual part 4 from Pennsylvania Department of Transportation, which is the one that we use in Pennsylvania. And what they did is they took AASHTO, but they modified, for example, the part of rock, right? They said you can only have micropiles that are founded on rock and things like that. I have the honor that I'm co-author of the bridge design manual from the state of Delaware. So in 2015, we put together this manual, and then we also allow micropiles, and we put some specifications for the special coastal consideration.
Which year, doctor?
The original was 2015, the one in Delaware. But since then we have, I know in 2016 we have a new version. I think since then it has been one more update. Though all these manuals, except the AASHTO one, all of these are available on the internet. Like if you Google them, you can find links to the PDFs. Except AASHTO. AASHTO you have to pay. It's the only one that is not free. And then I have another reference there that is pretty good, which is the Colombian. It's called CCP 14, which is the Colombian code basically for design of bridges. It's a translation, literally it's a translation of AASHTO from English to Spanish, and from English units into international units. And I say it's extremely useful because even if you are not working on Colombia, it's a free copy of AASHTO that is already translated. So it is a few versions. It's a few versions before.
We need someone who speaks Spanish like you. I mean,
exactly.
It's difficult for us to understand.
Yes, correct.
But so, at least we can see the equations, the tables.
You can see the equations for free. You don't have. I think AASHTO is about $1,000, so you can save some money. But also, I mean, I do a lot of presentations and events and things like that in South America, and I always refer to this. Even if you're not in Colombia, it's a good document to have. So everything we're going to talk today is the same on all these manuals. I mean, my point here is that the design of this is highly documented. This is not, when we did the presentation on slope stabilization with the foundations, I was mentioning a lot of these things are not on any manual, right? Like the papers that I have wrote have become some standard in certain areas because there is not a manual that is taking all this. There is not a code. In Micropiles, it's a different story. There is complete documents already done. So let's start defining what are the parts of the micropile. We mentioned a little bit before. So what you have there is a cross-section of a micropile. You have a case section and an uncased section. You can see the casing like that cylinder going down. You're going to have a central bar, and there is two types of central bar. One is called the stinger, the other one is called continuous. Why there are two? Because depends if the micropile is working on tension or compression.
So will you be slower about this? What is a stinger and the bond?
Yes, correct. So let me just put the laser here. So you see the laser here, right? So this here is the casing, right? So the casing is going into rock or soil if you're working in an area that accepts soil, but it's going into the competent strata. So that's going to be the case portion, and then the part that doesn't have the casing is the uncased portion. Now, this is the central bar, which is here, right? Now, depending if it's a compression or tension micropile, these bars may go all the way. Right now, the way that AASHTO designs micropiles, if you're doing a tension micropile, this bar has to extend all the way into the pile cap. So basically, if the micropile is going to be subjected to tension, you assume that all that load is going to go on the central bar, and then it is going to be transferred to the bond zone. Now, if you're doing a micropile in compression, because you are working on compression, you don't need to extend this bar all the way to the top. You only extend it, typically it's about 6 feet from the bottom of the casing. So it's basically you have an overlap of about 6 feet between this central bar and the casing. And then contractors typically call that the stinger, because it's like a stinger on a bee, right? It's just something that is going from the bond zone and getting into the casing. So that's the difference between the stinger and continuous. So again, continuous if it's on tension all the time, and then a stinger if it's just in compression. Then there is the plunge length, which is what we were talking, is just kind of like embedding the casing into the competence strata. The only reason that you do that is so when you start grouting, you don't lose grout, right? The grout doesn't go around and goes up. And then you have the bond length. Now, one thing that is interesting in this detail, and it shows how micropiles have changed in the last, I don't know, maybe 10 years, 13 years, is that before the bond zone, you used to extend the casing into the competent strata, and then the bond zone diameter used to be the inside of the casing. Because basically, if I advance, right, if I'm advancing my drill and I'm advancing my casing with a traditional tool, the hole that I'm making, the diameter of that hole has to be the inside of the casing. That was the way that we started doing micropiles. But then a new piece of technology came along, which is it's basically an eccentric bit that when it passes through the casing, it opens. And it has the capacity that you make a hole that is even bigger than the casing as you go down. That gives you a bigger bond zone, a bigger diameter bond zone, which means more resistance. That's the reason that in these details, you can see that the diameter of the hole, of the bond zone, is actually the outside of the casing, right? And sometimes that at the beginning is hard to understand. And when I show this to the engineers that work with me, then they say, 1 second, but if you stop the casing at some point and you continue with a diameter that is bigger than or equal than the casing, while you continue drilling, how that casing doesn't fall into the hole, right? And I always say, yeah, but contractors are very crafty. So what they do is they can put like a wrench on top, right on top of the casing. So
nice way. This one, if they have such a technology, that's very good because you keep the diameter unchanged.
Exactly, and it's
or
just
even enlarged, as you said. Yeah,
correct. And then just to hold it, you can put a wrench, or you can weld plates that go into the casing and don't let it go below. Like basically, the ground surface will stop. So once you have this, you have the bond zone. The typical length of the bond zone is between 10 and 20 feet. And that's an interesting concept because sometimes people say like, why is limited? Why can I just do a bond zone that goes forever, right? Why can't just go 60 feet, 100 feet? But it's the same thing that when you're doing, like anchors. When you start, let's say that this is tension. When you start putting tension on this, the load goes into the bond zone, and then the top of the bond zone is going to have, it's going to start putting the shear stress, right? It's going to have the resistance, and that area goes into peak resistance. The more you pull, that peak resistance start propagating down. The entire bond zone end up being on peak resistance. Now, if you make a bond zone that is too long, the moment that you get peak resistance at the bottom of the micropile, at the bottom of the bond zone, the front,
you lose resistance at the top.
Exactly. You pass from peak to residual. So that's the reason you typically control this to about 10 to 20 feet, right? So again, it's just the analogy of an anchor. So, and then, okay, so then once you have the bond zone, let's just do 2 cross sections, which is what is shown here on the right. So section AA is basically a cross section on the casing. So the way that you see it is you see the casing here. Typically the casing, it's half-inch thick. The original casing, it was really reused pipe from the oil industry, and it was what is called the N80, and it's a pipe, right? And now it's, it was secondary use because it came from the oil industry. Now it's brand new. Right now, like you just buy it new, but but it's typically a pipe that is about 7 inches, 9-inch diameter, half-inch thick, 80 KSI steel, right? And that's gonna be your casing. And then in the inside, you're gonna see a bar. These days we work bars between number 20 and number 28 in English units. So that's 20 divided by 8, inches. So that will be like 2.5-inch diameter to a lot more, right? And that's what you will see on the case section. And then on the uncase section or on the bond, you're gonna see pretty much the same.
So that's almost like 42, 44 millimeters up to 60
yes, correct.
millimeters.
Correct. And and then when you are on the bond zone, you have the same, but you don't have the casing. So you are just gonna see your bar and you're just gonna see the grout around it, right? So that is in general.
No, it's more than that.
Let's do the conversion. I have my calculator here.
You said 2 inches or 2.5. What did you say?
2.5, because it's 20 divided by 8.
2.5. We're talking about 60 millimeters.
That is 60. Yes, correct. 63 millimeters.
So it starts from 60 millimeters.
Correct. And then 28, which is the biggest one, that is 3.5 inches, right?
So we're talking about 90 millimeters, 88.
Yeah, that's 8.9 centimeters. So yeah, basically 9 centimeters.
So we can't have a micropile with less diameter.
No, you can. I mean, you can, but it's just that is not what is typically seen now, because we try to use more and more capacity, right? We try to load it the more that we can. So you can always use, I used to do micropiles with smaller bars. It's just that now the loads are growing.
Why we don't go to very small diameters? Why don't we?
To smaller diameters?
Why do we stick to a large diameter bars?
Yes. So bars. Okay. So it all goes into, because remember, this started, there is a lot of going into a name that is micropile, right? This started trying to, and this is what I said, it's interesting to see the evolution of the technology. Because when we started, it was micro, it was small loads, it was small things, right? But then what is the cost? Look at it this way. When I'm drilling, the cost that imagine that I have 60 feet of soil and then I go to rock. If I'm drilling through 60 feet of soil and then 10 feet into rock, what I really want to do, instead of doing a lot of elements, I want to do less elements with more into rock and more capacity. The more capacity I can have in one element, the better, because then my cost is less. It costs me less to do deeper holes, but a significant less number of holes than do a lot of holes that don't go deep, right? So because of those economics, you want to maximize the capacity of your micropile. So when you are talking about these diameters, literally what we try to do is let's put a bigger bar that allows me a higher structural capacity. The higher structural capacity that I can, the longer my bond length without exceeding the 20 feet, and I'm optimizing the foundation. So it is really more for economics and trying to make this cost effective than anything else. There is nothing wrong to put a smaller bar. It's just that if you put a smaller bar, your resistance is going to be less, your bond length is going to be less, and you're just going to need a higher number of elements. So that's really all the, all the reasons. There is absolutely no problem doing something smaller, right? You can even reduce the size of the micropile itself, even if you reduce the bar. But it's just the economics, how they end up working out. Now, the capacity, that's what I said, it has evolved. We used to do micropiles of 50 tons. Now we do micropiles of 250, it's the numbers have increased significantly. So, all right.
Is it in any way related to buckling of bars?
That's another thing. Typically, and this just comes straight from FHWA. So FHWA considers that if you have a micropile that is supported on soil, on the surroundings, like if I'm drilling through soil or if I'm drilling through bedrock, it doesn't really have any problem with buckling, right? As long as you stay with the typical diameters. We actually have to analyze it once, because when you pass, let's say when you pass karst topography, or when you are passing through abandoned mines, and your micropile is going to have a length that is not supported by anything around it, then buckling is a consideration, because this is a very slender element, right? So in FHWA is explained in detail. We end up doing that calc for the typical micropile, about 7-inch micropile with a number 20 bar. We found that you can have easily like 7 feet of unsupported length, and you are still not failing in like the Euclid, like the Euclid short column kind of, buckling thing. So as long as you have support on soil or rock, buckling is not a main consideration. But the moment that you start passing through voids, then you do have to be aware of buckling, and it's a potential failure mode.
It will be very effective when you have a part of the pile above ground. Then that will be dangerous, really.
Exactly.
You need to check buckling that time.
Correct. Like you never see micropiles going like that, exactly for what you said, because then buckling
usually they're underground, used
always
for
underground, always supported by soil on the side.
Why do we use micropiles, Sebastian?
Why do we use?
Yeah, why we go to
that's a good point. That's a good point. So I always say honestly, micropile should never be your first start. Like, let's just talk deep foundations in general. To me, your deep foundation, always, you should start with a driven pile. A driven pile is a proven pile. A driven pile is an easy pile, right? You put it on the ground, you hammer it. By hammer it, you know that you got refusal. You know the pile doesn't advance anymore. And if you do a PDA, a pile dynamic test, just with the PDA, with the attachment and CapWap, you can know the capacity of that pile. So to me, a driven pile, honestly,
my friends in US are not, some of them are not using CapWap. They're using this sweep.
Yes, correct. I mean, you can do signal matching with CapWap, or you can do just the PDA. But what I'm saying is, it's a proven pile, and you get capacity.
I just don't want to be I just don't want to be advertiser here.
Oh, no. Of course not. Of course not. So, but okay, even if you are not using any of that, even if you are just driving the pile and seeing that they has refusal, right? You have a pile that is that it went and is not moving anymore. Now, the problem is you cannot do driven piles everywhere, right? If you are working in a city environment, it's
maybe you're not allowed to do it.
And the more the time passes, you are not allowed, right? If you are in a city environment, you cannot induce vibrations. I mean, driven piles induce a lot of vibrations. It induces a lot of noise. You also have a lot of noise
through that vibration.
Yes. So if you cannot do that now, another scenario that you can have is, imagine that you are driving a pile that is going to rock, but you are in an alluvial deposit and you have massive boulders and oversized things. And, then you cannot drive it because it's going to get stuck, right?
Yeah,
I mean, you start driving.
It will stop somewhere.
Another reason, it may be that, your distance to rock is not enough. And typically, you cannot use a pile less than 10 feet long, right? Because then it's just too short. So if you have reasons that a driven pile cannot work, typically then you move. I mean, and I'm talking already on the premise that you need deep foundations, right? That you could not just do a spread footing and get done. So if you cannot use a driven pile, then the next step in my mind is typically some kind of pre-drill pile, right? So you can try to do a pre-drill element, like, you can try to do, I mean, you could do an auger cast pile, but auger cast piles are not accepted in transportation, but you could, if it's not transportation. Or you can do, a little drill shaft or something like that. A little drill shaft probably has a high capacity, so you reduce the number of elements.
You mean by auger cast piles, you mean continuous flight auger, CFAs?
Yes. Yeah, so CFAs are not accepted by AASHTO yet. So it's a really good pile, but it's just you cannot use it on transportation typically.
I don't like them also.
You don't like them?
Then.
I like them. I mean, I have used them. I have used them a lot in private projects.
But it is practical, in fact.
It is practical as long as you, I mean, obviously, the quality assurance, it's hard, right?
You need more quality control.
But if you provide redundancy and you do a lot of them, then you compensate, right? So yeah,
it's fast, very fast.
It's very fast. It's very
easy
fast.
to work.
Correct.
What are these figures?
Yeah, so okay, so if you cannot do any kind of pile like that, right, then you end up coming to micropiles. So it's a process to get to micropiles. You could not do certain piles before. You have limited space, you have obstructions, I mean, let me put it this way. You need to have a reason to do micropiles. Micropiles should not be the first thing that comes to your mind if you're doing a deep foundation. So if you have those things, then you come here and then you come to the place to design them, right? So the way that we design them is based on FSWA, and it's also based on AASHTO. There is the geotechnical design, and then there is the structural design. So let's start with the geotech design. Both are very simple. The geotech design, you are only designing the bond, right? So what you do is different manuals, depending where you are, local codes are going to give you a typical range of a ground bond strength. So for example, in this case, if you are doing the micropile in soft shale, the stress that you can use as bond, it's 30 to 80 PSI, right? If you are, let's say, on sandstone, it's about 80 to 250 psi, or 0.8 ksi to 0.25 ksi, right? Multiply by 1,000, you get psi. So those are the values that you use as your ultimate geotechnical resistance. Then you take that, and what you do is that you multiply. So you need the surface area. So you take the perimeter of your bond zone, multiply the length of your bond zone, multiply by this value, and that gives you the force. That's your vertical resistance, your axial resistance of the micropile. Then you take that and you multiply them by like a resistance factor, because you are doing LRFD. So that resistance factor could be something like 0.55, 0.6. It's obviously a number less than 1 because you have a fraction. And then that becomes your factor geotech resistance. If you are working in an area that you are using factor of safety instead of LRFD design, then what you do is that you take that and divide by a factor of safety of 3 or whatever your local code is indicating. So that is the design of the bond. Now, these stresses, I put a typical value there, but you can have also for soil, if you are working in a place that you can have micropiles on soil. And then there is different in AASHTO, in chapter 10, there is different table depending on the installation method. If these values that I'm showing are the typical ones for gravity feeding micropile. Basically, you have a tremie pipe, but you have marginal pressure just for gravity to go down and the grout to get into the micropile. If you are doing pressure grouting, you can use higher values because now you're pressure grouting the bond, so it's trying to expand, and the pressure is making the grout going into a lot of places. So you can go with a higher value of grout to ground bond strength. So that really takes care of the geotech part. It's very simplified, very streamlined. Now the structural part is even easier because the structural part is just the resistance of a column. So it's these equations that we use for everything, which is the combination of steel and concrete. If you are let's start with the easy one. If I'm designing in tension, as I mentioned before, the only element that is taking load structurally is the bar. So then my resistance is the area.
You will not include the casing.
Correct. Well, exactly. In tension, you do not include the casing. If you are designing in tension, is just the central bar. So it's the area of the bar multiplied by the yield strength, right? And then multiply by.
Is it because of the construction method? Because the bar is the one which will enter the concrete, and you have the plates on it.
Correct. That is the reason, but I will refute that concept in a little bit. I'm telling you the AASHTO design, and then I'll tell you my personal opinion. So in the AASHTO design, that's the way you do it. So you take the bar, area of the bar times the yield, and typically times 0.8 or some kind of factor. And then you take that and you multiply by a resistance factor 2, which is just going to be, or divide by a factor of safety. Basically just reduce that value. Now, when you are so that's in tension.
What was that? You multiply 0.8 by what?
So typically we used to do it the area times the yield times 0.8 just to reduce it.
What is yield?
The yield stress. So like, let's say the 50 ks, I mean, in this case, typically 75 ksi. The yield stress of the steel, basically. The point that the resistance increase and then becomes plastic. The yield.
Yield.
Yes, correct.
But
yield.
We will not use the ultimate?
No, typically on this you use yield, not ultimate, just yield. Yes, that's an interesting concept, that it is. I mean, typically AASHTO requires yield and not ultimate.
And you multiply it by 0.8?
By 0.8, correct.
And then you multiply by a resistance factor?
Yes, and that has changed in codes, because the tendency is that most codes are dropping that 0.8 and say, no, just give me the yield, multiply by the area, and that's my ultimate, and then I multiply by a resistance factor, right?
Okay.
But we used to have that 0.8 for many years. So that is when you are doing it on tension. Now, when you are doing compression, then it's typically two separate calcs, because in compression, you have the resistance on the case portion and the resistance on the uncased portion. Now, why you have two calcs? Because on the case portion, you do not have the central bar. So you only have the steel of the casing plus the concrete. While on the unbond, in the bond zone, you only have the central bar and grout. You don't have the casing, right? So in reality, it's very simple, because in the majority of the cases, the bar area is less than the bar, like the casing. So you can clearly see, I mean, you are required to do both, but you typically by inspection can eliminate one. And then, that equation, it's the usual one, which is what is the area of the concrete multiplied by the F prime C for the concrete is basically the not the yield because it's concrete, but it's basically the maximum stress that the concrete can take. So it's the area times F prime C.
Do you check any bearing stresses between concrete and the pipe?
No, so that's okay. So the general way to calculate is just the area of the concrete times F prime C times 0.85, similar as a column, plus the yield of the steel times the area of steel, and then all of that multiplied by 0.85.
We're talking, this one is a structural design.
It's a structural design as a structural
capacity
column
of the section.
Correct. It's just the structural capacity of the section, yeah.
But at the top, is it really the load? Is it transferred to these three parts, or it is mainly transferred to the pipe?
So, AASHTO, and I'll be careful on my statements. AASHTO assumes that it goes like that. AASHTO does not assume that there is any failure between casing and concrete. I agree with you. I think the more you instrument this, the load goes where it's more stiff and probably goes more into the casing that you give credit. But given the resistant factors and everything that we have,
so we don't check really the bearing stresses.
No, not really.
The pipe and the concrete.
Not really. I did it once because same as you, I was like, this doesn't make. I mean, I don't know. I wanted to see it. AASHTO at the end has the bond between.
I'm just asking. Don't say like you. I'm just asking.
No. But what I'm saying is, when you check, you end up finding that bond between casing and grout, it's high enough that it justifies this assumption. I think
just
it's
for your information. I did micropiles in my life, but not as a project, a full project of mine. What I did usually, I go to micropiles when I have underpinning.
Yes, correct, underpinning. Because
the machines are small, I can push them inside the building. And I drill a couple of micropiles, replacing a failed pile or strengthening some area. That one I did, but generally like a project like yours, this one I never did. So
correct,
and that's because what you do and what I do.
Correct, because that's the way that it started.
I don't want to take any responsibility here.
No, because the way that it started, it was like that. This was done for underpinning, right? And then little by little,
I use it for underpinning. I'm happy to use them for underpinning.
Correct, and then the underpinning took over, right? I mean, like took off, and they became like brand new foundation elements, not only for retrofitting, but also for design. So yeah, so this is really the part. So it's very simple. I do have some thoughts on that because after doing 20 years of micropiles, I was in some disagreement. And again, I want to be careful in this because if you design them by code, when you are doing tension testing, the central bar is the one that takes everything, right?
Yeah.
But the more that I think, when you have the micropile going into the pile cap, and you typically put some kind of plate, you have your casing going, your bar, and then you put a plate and a knot, right? So when you pull the pile cap, it's going to develop a shear cone in the concrete, and that's going to come the resistance. To me, it was not very clear, or there is, I don't know, to me, it's not that evident and obvious that the load is going to go all into that central bar. So I start posing the question, how do you know that there is no load that goes into the casing, right? Now, if it goes into the casing, right, if you pull the casing, imagine that you don't have a central bar. Imagine that you only have a stinger, and you pull the casing. If you pull the casing, right, there is going to be shear between the casing and the grout, and that shear is going to happen, and it's going to pass the load all the way to the central bar. Then there is the stinger, right, on the bond zone, and then there is going to be bond between that bar and grout, and that force is going to go back into the bond zone.
It will transfer the load to the bond zone, yeah.
Correct. So I have this, and it's not I don't want to sound like a crazy person here. It's not a revolutionary way to look at it, right? So
but how do you ensure the connection between the steel pipe and the concrete?
Yes, but just analyzing it based on bond. Like AASHTO has the values between grout and casing, right? I mean, basically.
No, I'm not talking about the concrete, grout concrete. I'm talking about the foundation concrete.
Oh, yeah, because typically,
how do you be sure that you're pulling up the casing.
Correct. So typically the way that you do it is that you put a plate. So when you have the pipe, it goes up with the, let's say, you know, either with the bar or without it, and you put a plate, like an 8-inch by 8-inch plate. And what it happens is that when you cast your pile cap, right, that plate is completely connected. So when I pull the pile cap up, that plate is going to develop a shear cone inside the pile cap, and that shear cone is in concrete, and that is really like the same as designing the facing for an anchor wall. It's basically that shear in the concrete is what is going to hold it, and is going to bring the entire plate and the entire micropile up, right? So if you don't do that plate, you cannot rely between the casing and the footing just on that, because that's not going to be enough to hold it. You need to put that plate and create that cone.
Will you weld that plate to the casing?
Yes, you can weld it in this case. So exactly. So that's what we did. So I have this theory that you didn't really need the central bar if your tension test was low. So we did tests exactly describing what you did, what you were mentioning. We put a casing, we put a plate, and then we pulled the entire thing up. And what we demonstrate in doing the math is that for forces that are small, you do not need that central bar. So we did this test. We actually have it on a project. It was a small project. And we put together this paper in 2018, I believe. So it's almost 6 years now. And we put it and we demonstrated it was great, because to my knowledge, it's the first time that somebody was kind of challenging a little bit the way that ANSTO is done. Now, I don't want to send the wrong message. This paper is great, but this is not a code. This does not replace ANSTO. This is just something that is interesting to think about it. What I saw that it worked is that many contractors start using this paper, because it was a way to justify that if you have a very small tension load, you can save that central bar and just weld the plate on the casing, and then you take care of that. A very interesting point that was brought to me, because we published this in the Deep Foundation magazine, and then we have a discussion on this on the DFI National Conference in Chicago, is that you got to be careful too in some respect, because the theory works great, the test show that is great on small loads, but when you go to higher loads, remember, this is threaded connection for casing, right? You got to be careful that the connection on the thread casing is able to take uplift forces. Typically, these threads on the casing are designed to take compression loads, right? So obviously, the casing is only as strong as the connection on the casing sections, right? So if they are not designed, if they were not manufactured on that part, to connect, to resist the uplift, that's going to be the failure of your system. So I always like to point this. It's a free paper. It's online. It just needs to be taken with some cautious, because again, it's not a code. You always have to follow a code. This is just a way that I always said, if you end up in a trouble that you need to have a micropile that has tension, that doesn't have a central bar, this could help you, right? Just understanding the theory. So, but anyway, moving on. So let's start looking into how you construct it, and then a lot of these things.
Let me ask something about the test. You're using two beams here, and with a gap between them to pull out the bar, the central bar. But it's not showing, because so that I explained that to the audience. So you have the jack in the middle of two beams, and there's a gap in between?
Yes. So let's do this. Hold the testing part, because I have a whole section of just testing, right?
Okay.
So let's go through this section, and then I'll go back, because I want to explain the whole setup of the beams and the whole thing. So, okay, so the first part, let's just construct it, right? So this
is a big machine, huh?
Yeah. Yes. So this one is not a small one that you are going to put on a basement for retrofitting, right? This is not going to be for like a small underpinning or something like that. So most of the rigs that you have now are track rigs. They are typically operated by remote control. There are smaller ones, like the original ones were smaller ones, because they were going in basement, they were going under bridges. Now that we are drilling bigger and higher loads and all that, they have become bigger. So this is for a job. You can see this is the first micropile on the job. So we're drilling. This is pneumatic compression air going down, right? And then you are drilling. Once you have the hole, then this is another picture. You can see like the pneumatic and all that. And I mean, sometimes you use water, sometimes you use air, depending. And you basically drill. You advance the casing. This is the casing. These are details of the casing. The casing typically has this little teeth because if you rotate it, it can also help. What you see on the red square there is this pneumatic jaw that I was saying, this eccentric tool that when it goes inside the casing and passes through the casing, it goes to the other side and opens, right? It's an eccentric tool that opens and it gives you a diameter that is bigger than the casing. So it's what we were saying before, that now you're making bigger holes that are more efficient. And then when you see on the left is the central bar. Basically, that bar is gonna, once everything is installed, that bar is gonna go in the middle. So this is basically the technology. You have the casing, you have the tool that opens and keeps going, and eventually you're gonna put the bar.
Is that bar smooth or threaded?
No, so typically it's let's see, on this one is threaded. I mean, it may be hard to see.
It's a threaded one, huh?
Yes, typically we use thread bar.
And it looks like 60 millimeters, really.
Yeah, this one is probably smaller. That's an old picture, and I think at that time we were using a smaller micropiles. You're gonna see a few pictures later on that is big, and also we typically.
How long usually typically are the casing pieces?
Typically 10 feet, so they can come in 10 feet or 5 feet, right? So you can, depending on what you need. If you don't have a limitation, typically it's 10 feet. If you have limitations on like overhead clearance, then you can go 5 feet. So, you drill, you put the permanent casing, you go inside. There is two ways to do it. Before we go to some point, we stop the casing and then we drill, right? But typically, most of the time, you advance the casing and the bit together. You go to your bond zone, and then once you confirm that you have your bond zone, then you lift your casing. Why I say that? Because what you want to see is that your bond zone is not on an area that has voids or soil seams or anything like that. If you have a good rock like a sandstone or something like that, that's fine. I mean, you are not going to expect much surprises, but this is done a lot in karst topography. When you have voids and soil seams and things like that, it's perfect because you pass through all that junk and you go to a good strata. So the way that you know if you're on good or bad is basically the torque resistance, the penetration rate as the micropile is being drilled. The operator typically has a good eye on like, okay, what is my rate of advancement? And if I see a sudden drop, that corresponds to some kind of void or some kind of soil seam, right? So typically you go, and then once you have, let's say that my bond zone was 10 feet. Once I determine that I have 10 feet of competent material, then I stop and then I lift the casing, right? And then once I lift the casing, that's going to be the final location of the casing, right? I retrieve the drill bit, I lower the bar. If it's continuous bar, then you lower it. And, if it's just a compression, then you just put the stinger down. And then once that is done, then you grout it, right? Now, the specifications always talk about control manner. Sometimes it's very loose because they just say lower the bar in a controlled manner. What I'm showing there is a controlled manner. It's in a perfect sample, right? You just take some kind of, you can just put some kind of rope and just lower it or some weights. I also have been in some projects that the contractor didn't care and they literally just put it and release the bar, right? And to me, I was like, that's not a controlled manner. You don't want a piece of steel that is 16 feet long or something like that traveling, by acceleration of gravity in a hole and go to the bottom. So I typically tend to be very careful about the control manner. And it's like, you have to place that bar in a good way. So once you have that, right? Okay, so these are more examples of lowering the bar in a controlled manner. You can see a few things on the bar that is on the right side. You also have the centralizers, which are those white balloons or balls or whatever you want to call it. The only thing they do is that when you lower the bar, it just keep it center, right? So when you put the grout and all that, it's just going to keep it center so you have enough cover of grout around it. So, that's just the way that you want to do it. So now is the testing part. So I'm going to just talk a little bit about the testing that we do, and then we go into the apparatus and all that. So there is different kinds of testing, two main ones. The first one is verification testing. So this is similar to other deep foundations. A verification testing is typically 1 or 2 per substructure, right? If you're talking bridge design, it's going to be 1 or 2 per local substructure, per local condition. They tend to be sacrificial. You typically don't count them as the production ones. They are done at the beginning, and your idea is to take it to about 2 times the unfactored load, right? So I take my load, I take any load factor from LRFD, I just take an unfactored load, and I want to test it to 2 times that, because I want to have a sense of confidence, reliability on this system, that I can go to a really high load, way higher than I designed, and it's going to still be fine. Again, that is in very limited number of piles, typically sacrificial. Then you do proof testing. Proof testing is different than verification because this is actually on production micropiles. You typically only do about 5% of the production micropiles. This has changed a lot. Initially, that 5% is what FHWA was recommending. I believe that is on the FHWA manual. However, with time, this has changed because the more we test micropiles and the more we see that they always work, now is reducing, and it's kind of combining verification and proof testing and say, just do 1 or 2% of structure and that's it. And it doesn't even have to be a sacrificial element. Just do it on a production element. But traditionally, the proof testing was only done on 5%, right? And it was taken to 1.6 the unfactored load. You did not want it to take it as high as the verification, but you wanted to go at least to, like the factor load. So if you assume that all the factor loads combine to about 1.5, then you are testing it pretty much to your factor load or very slightly above that. So that is like in summary, the two tests that you can do. They are done with the same frame. They are done with the same equipment. It's just a definition of the load that you put on that. Now, you not only go and put the load, right, and go to the maximum load, but you also want to hold the load and do a creep test, right? So the creep test, depending if it's a proof or a verification, can vary on time. Typically, verification testing, you leave the load for 60 minutes and you analyze what is the deformation of 60 minutes. If you're doing a proof one, you do a reduced version of that and you only do 10 minutes and see that you don't have. And that's going to enter into the acceptance criteria. But that's pretty much just the way you do it. So now let's talk about the equipment, and then we can talk about the acceptance criteria. Because this is not straightforward, and I'll tell you a lesson that I learned with a high price. So the typical setup of a micropile, it all depends if it's tension or compression, and it's extremely important. When I started my career, I did not understand why it mattered so much if it was tension or compression. I was thinking, the way that I always saw is, if my micropile is designed in compression, I want to test it in compression, right? If it was designed in tension, I'll test it in tension. Now, I'm going to explain why one test, it's a small difference, compression and tension. It doesn't sound like much, right? One test probably costs 5 times the price of the other. And it's all because of the constructability. And this is what is extremely important to understand, regardless from the design point of view, right? So the way that the test is done is that you have the pile coming up, right? Even if it's compression or tension, you need to have a central bar just so you can grab to the jack, right? So you have your bar coming from the micropile and it's going all the way up. And as you mentioned before, Ahmed, you have 2 beams. One beam is at the front, one beam is at the back. Your micropile is going through those, and then it passes and you put a plate, and then you put the jack on the top part. This itself, it's a tension micropile because the jack is right here, right? You have the jack here, so you have one beam, one behind. The micropile bar is passing through, and then you put your jack, and then you put this plate.
This jack is having a hollow part.
Yes,
or
a hollow
in the
center, correct. And then the bar goes through the middle, right?
So the jack is a cylindrical.
It's a cylindrical shape, correct. And this is the same technology that is used to test like ground anchors, right? It's actually
the same in ground anchors.
There is a lot of similarities. Ground anchors and micropiles are done with the same machine, pretty much. They have similar size, and they are tested basically with the same equipment. It's just that one is horizontal or almost horizontal, the other one is vertical. So yeah, so you have the hollow jack, and then you have the bar, and then you put these plates, and then when the tests start, this is a tension microbar, because when this opens, the jack is going to open, right? When it opens, it's going to push this up. So that's what it makes it a tension micropile, right? It's pushing, it's pulling up, right? It's to the sky. So that's tension micropile. But then what happened because there is action reaction. If I'm pushing that up, I'm also pushing this down. So basically, I'm pushing the beam down. As I push the beam down, that is going to go to one side and it's going to go to the other side. And it goes as a compression force. So what you need to do is you need to put this kind of cribbing, you need to put these wood pieces to develop some kind of footing. So when this pushes down, basically this just doesn't have a failure, like a bearing capacity failure or excessive setup, right? Now, obviously during the test, you're going to monitor, you see here, there is 1, 2, and 3 little dial gauges that you are going to see to monitor the deformation of this. And then you also have the piano wire, which is a little wire that is hard to see, but it's a wire that is going to pass through here and then there is a little mirror there, and it's just to have like a secondary thing to see, if one of the gauges stop working, you just want to have redundancy on your readings. So that's the way that you do a tension test. Now let's see what will change if I want to do a compression test, because that's the key to understand the difference between the two. So for a compression test, I need to now push the micropile down. So I do the same elements, but now I don't put the jack here. I put it actually below here, right? So if I move the jack from above the beam to below the beam, now I'm pushing the micropile down. But when I push the micropile down, that means I'm pushing the beam up, right?
Yeah.
So now the problem is that if I push it up, what is going to hold it so the beam doesn't go and fly in the sky? So I need to put, instead of this and instead of this cribbing, I need to have some kind of plate here that is welded to this or somehow connected, and then that has to have reaction, right? Reaction piles.
Yeah.
What are going to be the reaction piles? Well, more micropiles, correct? So you want to have, typically you put one here, one behind, another one here, and another behind. So to test one pile, I need to construct 4 reaction micropiles, right? And then this is going to go into an interesting way, because obviously if the contractor has to do 4 reaction micropiles to test one, the cost of the test is going to be significantly higher than if you are doing a tension one, right?
You can do a cartilage. You can.
Yes, correct.
You can build up a cartilage.
Exactly. So you can do different things, but it's more complicated because you need to take care of a thing that wants to go up.
It's expensive anyway. Yeah.
It's expensive. Exactly. So I go back to what I said at the beginning. I typically wanted to do compression tests because I was like, well, if I design in compression, I want to test it. Now, there is technical reasons why you want to do tension tests too. Not only the price. The price is a main consideration, and everything is money for a client. So you want to be cost effective, right? But there is also technical considerations that support the tension test even more. If I test in tension, right, we ignore any kind of end bearing capacitive micropile. The point bearing, right, the end bearing, we neglected. But in reality, is that there is going to be some, right? Either you account it or not, there is going to be some resistance. When you test in tension, there is no component of end bearing because you are testing in tension. So in some respect, if you think about it, testing in tension, it's slightly more conservative than testing in compression. And it's also significantly cheaper. So the way that I learned it is because I start doing a lot of projects and I always specify compression testing, right? And it was really only until one contractor told me, and it's like, hey, I know you always specify compression and I like it because I make more money. But in reality, think about the advantages of tension testing. And that completely opened my eyes. So every time that I do this presentation, I like to tell people, like, think about that. I mean, tension tests have a lot. I mean, it's faster, it's cheaper, and it's also conservative. So it has a lot of work.
I agree to some extent with this idea because we're talking about micropiles. But
correct.
If we're talking about board piles.
Yes.
With heavy reinforcement, tension tests are complicated, and they have a lot of confusing points during these tests. I hope I will present something about this in the DFI Super Pile 2024.
Excellent.
How we overcome the problems of tension tests on board piles. But
yes, correct.
I agree completely about
micropiles. Yes, correct. In micropiles is that, and it's also
only one bar. It's easy to push it through a hollow jack, and the test will be very smooth, and the results will be very nice.
Correct. So these observations apply to micropiles, right? I'm not saying that you should do tension tests on any other pile, because also if you are designing a pile that really relies a lot on end bearing, you should test it on end bearing, right? I mean, you should test it in compression. So, but those are kind of like the principles of the testing. This is another example. This is another. I mean, clearly you can see that it's a tension pile because you can see that the jack is on the upper part, right above the beam. So every time that you see the beam and the jack being above, there is difference with the one before. I mean, this setup, it's a lower pile, but similar results. You can see similar, like the dial gauges, and it's similar setup. So let's pass into the acceptance criteria. So these acceptance criteria, and we were having this discussion before, the way that you test on micropiles typically comes from the ASTM standard, the traditional D1143, which is compression, and then there is the other one that slips my mind the number, but it's the one for tension. The criteria has come from a combination of things. I mean, if you ask me, like, I know what it is on my projects because it's always on the DOT specs, right?
They should give it in the specifications of the project.
Correct. The project specification.
They should refer to which code or manual controls.
Correct. So, I mean, I believe they are included on the FHWA manual, but the different DOTs take them and modify them, and the different agencies kind of fine tune it. But the main is that you are looking at three main aspects, right? Regardless of where you're working, these three acceptance criteria will show in one way or another. It's slightly different. The first one is called the plastic elongation. So, because we want what we were talking before, you do not want your micropile to pass your bond zone to pass from peak to residual, right? You want to be always on peak. So typically the first criteria has to do with the plastic elongation.
So you don't want to see the failure in the bond.
Because if you saw failure,
pass the peak,
if you exactly. So what you do is that you measure the elongation, but what you get is not your total elongation. You measure total elongation, but then you subtract your elastic elongation. Let's say that I'm doing tension testing. If I'm doing a tension test and I'm testing a bar that goes all the way to the bond zone, I need to subtract the elastic elongation of the bar from the surface to the bond zone, right? So, and that is easy because it's just our typical equation of LP divided by A, the load times the length times the load divided by the area and the elastic modulus.
Yeah, the idea is clear. If you have zero plastic elongation, that means you're pulling exactly the whatever elongation you're getting is the elastic elongation of the bar. So it means there is a point that is completely fixed for that part.
Correct.
Which is usually not the case. If you have soils or rock, there will be some slippage, and you want to measure that slippage.
Yes, and the typical limit for that slippage, it's about 0.3 to 0.5 inches. And this is what we use on design of caissons. I mean, we went through this number on the previous talk that we have.
So we're talking about 4 millimeters to 6 millimeters.
Which is basically what Geotech has learned. That is what it takes to go to peak, right? And then once you pass that, then it goes down into, I mean, it's a conservative value to go to peak. Certain materials may take a little longer to get to peak. So that's the number that you want. So it's not the total deformation, it's the total minus the elastic has to be less than between 0.3 to 0.5 inches.
Yeah, usually in piles, we say if you have like 1% of the diameter, sometimes some areas they accept up to, I mean, not accept, I mean, they estimate that the failure in this confliction may reach up to 5%.
5%, that's what I say.
Yes. Yeah, usually it's 1%. So let's say if you have a diameter here of 7 inches, so the 1% of the 7 inches,
it's 0.07.
0.07 inches.
Yes, so this is a lot more generous than that, right? Because it's allowing it to go to between 0.3 to 0.5. It's kind of taking it a little bit not really related to the diameter of the micropile. It's taking it as kind of like as an arbitrary number. But then you also have to look
maybe for micropiles the criteria includes the cracking of the concrete, maybe.
Yeah, could be.
It's possible.
Yes, correct. So but then that's one value, and it's interesting because most of the tests that you do,
we understand that you want your plastic elongation to be limited to a value. Usually it is 0.3 to 0.5 inches.
Correct. And this is the way that you're going to see the specification most of the time. And then when you do the test, if you see a small value of deformation, everyone is happy. I have my secondary rule on this, and it's typically not on the spec, but I like another interpretation, which is I also like to make sure that the elastic elongation, okay, or let me put it this way. I also like to make sure that the total deformation that I measure is at least 80% of the elongation. So
I'm sorry. By the way, it is what we are talking about. It should be the total elongation. So if you have a failure, it's elastic plus plastic.
Yes, correct.
So when we're saying,
but yeah, but this criteria,
it doesn't work here.
The point, yeah, in this one doesn't work because what you are looking here is the plastic being between 0.3 and 0.5 inches, right? So it's basically you're saying take the total, discount the elastic, and you end up with the plastic, and that has to be on that. And then what I was saying too is I always like to make sure that the total is at least 80% of the elastic, because many times you do this and then you don't measure any elongation. But to me, it's like, okay, well, something is wrong because at least I need to have the elastic elongation. If I don't have the elastic elongation, it just means that I'm not putting the load that I think I'm putting. I'm pulling something different, right? Or I'm having resistance coming from another area that I was not considering, right? So that's the criteria for plastic elongation. Then the creep is very standard, is similar to anchors. This criteria also is an evolution of what we use on active anchors. What you are looking at is that you have at least, the maximum is basically 0.04 inches in 10 minutes. So I keep my maximum load, I keep it constant for 10 minutes, and I need to have a creep less than 0.04 inches. So that one is for the 10-minute interval, let's say a proof test. And if I'm doing the verification one, which is 60-minute creep test, I want to have a deformation that is less than 0.08 inches. So these values are just the standard that have been used for anchors all the time. And it's just trying to make sure that if I keep the load constant, I'm not just going to have a relaxation of the material and some kind of creep. And then the third criteria is just the pull-out failure, which is I'm looking at the last 2 points of my loading curve, and I just want to make sure that I'm still moving kind of like in a linear trend, right? I don't want to see on my last two that I went linear and then it becomes completely flat, right? Because then that just means that I kind of went to yield or I passed peak and it's going to fail. So in one way or another, you typically, the project specification will find these 3 criteria, right? And the way that it typically, the way that typically is done is that you satisfy the criteria and then you accept the pile. And then once you accept the pile, then you go to the next step, which is the connection. So we talk a little bit about the connection. And in this picture, it's exactly what you were saying before. You have the rebar, you have everything on the pile cap, you have the micropile going, you see the casing, you see the central bar. The part that is missing is the plate, right? So this micropile is not completed there. I need to go there, put a 8-inch by 8-inch plate and put a knot on top. And then that is going to really, take the entire pile cap and make it work as a unit.
Now,
so
isn't that the limit of the raft?
The limit of what do you mean?
I mean, it looks like this part, the one above the reinforcement, it looks like it's above the raft.
Yeah. They still need to go back and cut these down a little bit and, cut the bar, cut the casing, and then put the plate. They still have a lot of things to do to make it. And then on top of this,
you mean the plate? You mean the plate will be above the compression reinforcement?
Yes, typically.
Or it will be in between.
But this one is tricky too, because this one's for an abutment, and then you are actually having a stem. So part of this is going to also be embedded
in the concrete.
Yes, it's going to be an extension.
The reinforcement is not there yet. Okay.
Correct. This is not going to be flat completely. This is going to go like this, and it's going to have the reinforcement there. But in this case, you still need to cut the wire and you still need to cut a little bit of the casing and put that plate. But basically, you want to engage the entire thing, right? You don't want a casing that is not tied to anything and can just slip inside the pile cap. So, that is pretty much the process. So now the final product is, the typical consideration for the final product is you're going to have a bond zone. As we mentioned, typically it's on bedrock. Most of the applications that we talk or that we have been covering is for, is basically for axial elements. So, in this case, for example, what I'm there standing with my son, this is a picture on a project during COVID. That's the reason we have the masks. What you see on the far background, it's an abutment, and that has the micropiles, but it's mainly for axial compression, right? It's basically for vertical loads in bridges. Typical design loads right now that we work is about 200 to 400 kips, so that's between 100 and 200 tons. As I said, when I started my career, we were putting a tenth of that load, right? But now we are doing this.
That's really big.
It's really big. I mean, that's like, I am a big proponent that we should not call them micropiles anymore, because these things are monsters. You know what I'm saying? They are way too high. And then, as we talk, you can have compression load. I mean, for now, micropiles started as retrofit for tension. Now we constructed mostly on compression, right? By 2023, it's considered a standard foundation element. It's included on AASHTO, as we mentioned it several times, but it's an expensive element, right? So I always say, I mean, this should not be your option number one. In this particular project, the reason that we use micropiles is because this is in the middle of a city. We could not drive piles. It was also very tight construction. We cannot have noise. There were utilities and everything around. You cannot vibrate. You cannot produce, you cannot produce any noise or anything like that. And there were also obstructions. You needed to pass through existing footings from a previous structure. You literally needed to pass through a footing. So with a driven pile, you cannot do that. So because of all the pre-drilling necessary and all that, micropile was the way to go. In the main applications, you can have vertical and lateral loads. We also talked that about at the beginning, right? It's just the projection of the axial force. Very useful technology when you are doing pre-drilling and driven piles are not needed. It started as retrofits. It has evolved a lot into new. The picture on the left is just doing another test. You can see it's a tension test because the jack is on the upper part, is right above the beams. This is actually a good picture to explain what you were mentioning before of one beam behind the other one. Like if you look here, you can see one.
And also explaining when safety is not there.
Yes, exactly. This one was not.
This is very dangerous, dangerous setup.
Correct. So, and again, like I always like to take my selfies and put them on LinkedIn and all that. Take your pictures after the test, right? Once this is tested.
While testing, you stay away.
Exactly. While testing, you stay away. Once the test pass, then unload the pile, go there, pose, do whatever you want to do. But yeah, and then you can, in this one, you can also see the drill rig was right behind on the picture. So you have everything. So, it's a great technology in that sense. It's very proven. And I can never really finish talking about micropiles without talking about this bridge. This is a bridge that we did the forensic investigation in Colombia, in South America. We were not involved on the design. We were not involved on the construction. Unfortunately, I was just involved on the forensic investigation. And I think we mentioned a little bit about last time. I mean, it's kind of like a sad project. It killed 10 people. 10 people died as a result of the collapse of this bridge. It was during construction. You have this pier. It goes into a hollow caisson down there. And then on the other side, have this pier, the one that is collapsed. That's when I'm standing. And it also have another hollow caisson. It literally killed 10 people. It's very sad. They were working on this, and imagine this just failed. Basically, the entire pier just collapsed and went down. I was hired there to do the forensic investigation. It did not fail because anything related to geotech. It was a structural problem. And I'm very limited by court on what I can discuss about the real cause. The only thing I can tell you is that it was a structural element and not a geotech failure. But the reason that I like to bring it is because it shows the different applications of micropiles. In this case, the micropiles were used at the bottom of the caisson, basically where I'm standing. This is a hollow caisson with anchors there. So at the bottom of that, they constructed 90 micropiles in each one just to have the end bearing and to improve the material. It was in rock. It was in a phyllite that it was very fractured. And they used the micropile basically with a casing that have holes on the side. And they really used them more as a ground improvement, going back into Lee's concept as an injection tool rather than it's still a bearing capacity element, right? I mean, it's still taking load, but it was completely neglected in design. It was all designed as an end bearing empty shaft compared to that. So, and I like to mention this in the presentation because if somebody in Australia watches this presentation, they are going to believe that I'm insane because the definition of a micropile over there is very different. And the same thing in other parts of the world. The casing many times is temporary. There are many, many cases that don't even have casing because they have what is called, and it's one of the advancements that have been on the micropile and also like on passive anchors, which is a self-drilling nail or a sail drilling tool. So it's basically, you have a hollow pipe, right? And then you have a sacrificial head at the end, and a bit that start drilling, and as it goes down, it advances your bar. And while you do that, you also are grouting. So the more you go, the more you're grouting. And when you finish, you are done. You don't retrieve anything. It's a sacrificial bit. You have your pipe. You have that. So many countries have that definition of micropiles. That doesn't go into the definition of AASHTO, but that doesn't mean that is wrong. It is right. I mean, the loads are limited. You are not going to see 200 kips or 100 tons on those micropiles, but they still have their use, right? And they can be in soil. So it's a loose definition of what you really use outside the country. So it's a term that is still interpreted differently. It doesn't mean that it's wrong. It doesn't mean that it's anything. It's just different, right? So yeah, we just need to be aware of the local understanding of what the micropile is. So I think with that, oh no, sorry, I have more applications. So we also have land-based stabilization. So this was really the first video that we recorded together, which is basically using them to stabilize as shear pins, right? As shear pins to stabilize rock slides. So you can have it like that. There is a lot of, on that area, there is still a lot of research that is going on. I mean, what are the effects of battering them? What is the effect of putting a pile cap? You can increase capacity as we covered and then if somebody's watching this video and have not seen the first one, definitely watch the first one because it's explaining in detail how you design those shear pins, right? How that bar is going to be used as a shear element. And with that, obviously, that also has a paper that we talked last time. So I don't want to spend too much time there, but if you want to learn more step by step, you can watch our YouTube video and then you can also see the paper. And then in conclusions, it's a really good technology. It depends a lot on a subsurface investigation. I mean, you have to do a subsurface investigation, know what is there. As we said, it should not be your first option. But if you do a subsurface investigation and you find that you have problems like karst, obstructions, stuff like that is going to make any other kind of deep foundation very complicated, the pre-drilling aspect of your micropile is going to help a lot. You need geotechnical engineer involvement in preliminary, but also during construction. It's one of those techniques that, because the installation is so sensitive, you want to avoid any kind of grout takes that go excessive and all that. You need to have a geotech engineer involved. It cannot be something that a geotech engineer design and then disappears, right? It has to be all integrated into the same team. Identify risk and contingencies. One of the main things with micropile is the grout take. When I started my career, an excessive grout take was if it was more than 25% of the theoretical volume of the micropile. So you calculate the volume of the micropile, and if your grout volume that you install is more than 125%, right? So it's like 25% in addition to the theoretical volume, that was considered excess grout take, and the contractor was paid by cubic yard on that. That number was then refined to 150, and today it's considered to be 200%. So basically, I need to have twice the theoretical volume for the owner to pay extra to the contractor for that. And that is definitely the biggest risk on this. If you are in karst and all that.
Yeah, especially if you are in fissured rocks or jointed rocks.
Exactly.
Because you will have this problem.
Yes.
Sometimes you don't know. You have cavities, you have caverns, and unforeseen things in geotechnical engineering are very costly sometimes.
Correct. So that's definitely a risk to keep in mind. The importance of a specialty contractor. I mean, and with time, it's more standard, but at the beginning, when micropiles started, every person that had a rig thought that they qualified themselves as an expert micropile, and it's not. Doing a hole on the ground for exploratory drilling is not the same as doing a micropile. You need to know a lot more in terms of what is a standard penetration rate, how your rig is going, when you start grouting, excess grout, how to avoid excess grout. One of the main things that we are involved when you start having excess grout is what can you do? You have thickened the mix. You can start putting a little bit of bentonite so the grout stiffens and expands.
Do you know how much cheap became drilling in the COVID or even in 2008, for example, when the collapse happened?
I have no idea. Tell me.
They were even drilling for $6 or $7 a meter. It's around $2.50 a foot.
Yes. Wow. Yeah, that's insane.
$2.5 a foot, and they were knocking doors wherever they see a project or something. They knock the door. Can we drill for you?
Correct. And then that makes it dangerous, because if it's somebody that knows what they're doing, okay, that's fine. But you don't want to get stuck with somebody who has no idea.
I'm not talking about US or Canada. I don't know, but I'm talking about other parts of the world. I want to ask you two things that
yes,
you did not mention anything about them. The first is what kind of grout we use, and the second is what about corrosion?
Yeah, those are great questions. So thank you for pointing out, because I guess I intended to talk about it and I forgot.
And you have 2 minutes to answer.
Yes. So the first one is the grout typically just
take your time. I'm very enjoying the presentation. Yeah.
So so the grout typically just a standard cement water grout, similar to if you were doing a soil nail or an anchor. I mean, it's basically you want it to be very liquid that flows easily. So yeah, typically just cement and water. The typical acceptance on micropile is 4,000 psi, even though these days it has moved more into also 5,000 psi. So it's basically you want to have a high resistance, but it's nothing different than an anchor, right? Nothing different than any other. But the key here is that you are always looking on a mix of cement and sand. I mean, cement and water. You could put some sand, but there is nothing wrong about that.
The methodology of the grouting is different. When you grout an anchor, you have, especially a strand anchor.
Yeah, correct.
You have a pipe in the middle with starts pumping or starts grouting at the tip, and the grout flows upward.
Yeah, tremi pipe, what is called the tremi pipe, that you pull it up from the bottom going up, right? And
we don't pull it; it will remain there.
It will remain there until the grout goes out.
The anchors is like that.
Oh, you leave it. Okay. You leave it permanently
in the micropiles.
Yeah, so the micropile is similar. It's just that you remove the pipe. So basically, you put a pipe and you go from the bottom, right? Tremi pipe, and then you grout it all the way until the grout comes out, right? When the grout comes out,
so it's the same principle. You grout from the bottom,
from the bottom up, and then when you finish, typically you take the pipe out. You know what I'm saying? Like once everything is done, then you take the pipe out. You don't leave it inside. But it's similar.
Is it allowed usually to do some vibration for the grout?
Well, typically not, because you use it's like a very slurry, like cement and water. I mean, it's almost a liquid, right? So you don't really need to vibrate, right? Now you also do the quality control. You have to do interrupt air content, and you have to do the mode balance just to see what is the specific gravity of the mix, right? And typically the specs control that to make sure that you have enough cement, basically, that you have enough weight, which is represented by
you never
cement.
Added some gravel to this kind of grout?
No. So typically so that's the other part that I was saying on the, like, what do you do when you have excess grout? So for the most part, when you have excess grout, you start putting something like bentonite or something that thicken the mix, but without, like, the problem is if you start putting gravel and all that, I mean, you have a limited space between your bar.
I think sand is common.
Sand is common. It's just that.
But gravel maybe not used.
Correct. I mean, something that we do is that when you have excess grout, like I have done it on projects, we go back and we put, like, let's say the same grout with gravel, but without the reinforcement. You just throw it on the hole, pump it for a little bit, trying to penetrate the voids or whatever is causing this. Let it harden, and then come the next day and drill through that, and now do your micropile. So there are many,
like for stability of the hole, maybe.
Yes, correct. Basically, just trying to provide that. But in the ideal case, you don't do any of that. You just do, water cement mix and 5,000 psi, and that's it.
There's I think there's a good guide for grout mix design.
Oh yeah. This is all like a standard. Like in for example, in Pennsylvania, on the DOT, they already have the mix. I mean, it's already pre-approved and all that. So it's like you don't have to specify a mix, right? It's already, I mean, the grout technology has evolved significantly. So
I'm not sure if it is FHWA or it's long time I did not use it, so I forgot really. But I was using it. It has curves for the amount of cement.
Yes, correct, correct.
Water cement ratio.
Water cement
you
ratios
get how much is the compressive strength and things like that.
Yes, correct. It's a very standardized procedure, basically. It's not.
How about the corrosion?
Yes.
What
So
do you think?
that's what I wanted to show on this one. So typically, if you have in a corrosive environment, there is two ways that you take care. The first one is if you have a corrosive environment on your structural calcs, you are supposed to deduct 1/16 of the thickness of the steel. So basically, similar to any other pile, you assume because corrosion, you're going to lose some of the thickness. Now, that is done on the casing because you don't put epoxy coated or anything on the casing. So you design assuming a loss of 1/16 if you have a corrosive environment. Now, the central bar, if you have a corrosive environment,
1/16 of
an inch.
1/16
inch.
Yeah.
Yes, which is the same thing that we do for like driven piles. Like if you have a steel driven piles on a corrosive environment,
you're talking about
with that.
Around 0.7 millimeters.
Yes, let me see. So 1/16 of 2.54 centimeters. So yeah, it's about 1.6 millimeters, something like that.
1.6 millimeters.
Yes, correct. So you assume that is like as a sacrificial loss that you are gonna have for corrosion.
This is usually for a specific design life.
Like yes,
maybe
correct.
50 years or something.
I think it's something like that. Yeah, it's basically the AASHTO design life, which I don't remember exactly how long it is, but yes, because I always do the calc and think.
So if you have more design, more life you want, you need to have thicker.
Oh yeah, you can deduce more. Yeah. So, but that's on the casing, right? Now on the bar itself, if you have a really, aggressive environment, then you just epoxy coat it, as it's shown here. You see that it's green because it already has.
This one is epoxy coated, really.
Yes, and then you can see those bars on this side over there are also epoxy coated. So that is if you have a really corrosive environment. Most of the examples I believe that I was showing, like this one also, you see this one
also epoxy coated.
Yes. Yeah. But some of the other ones, like this, they are not.
Well, usually the grout is a good preventing.
Yes, I mean that's really my point. And I mean, the thing to me is if you're gonna have this, right, and it's gonna have a casing and it's gonna have concrete between the casing and the bar, that is a lot of corrosion protection. You know what I'm saying? I mean, casing plus grout, that gives you a lot. So if you have a very corrosive environment, then you put the epoxy. I don't know. I mean, I don't want to sound like I'm doubting the manuals, but I wonder how much really is necessary because I believe at that point you already have enough corrosion protection. But I guess better to be conservative. So that's typically the way that is.
Well, usually if you have deep deep environment, the corrosion will not be effective. But because micropiles usually are close to the surface,
yes,
they are subject to groundwater fluctuation. So they may have a problem with existence of a lot of oxygen.
Yeah, correct. And then that can,
We usually I've seen projects that we add even cathodic protection.
Okay.
To the reinforcement and to the micropile reinforcement. You can add cathodic protection.
Yes, absolutely. Yeah, you could always do it.
It's all cost. It's all cost and benefit.
Correct. It's
ratio. You should decide what to do for corrosion.
Correct. And what is your specific situation? So so that's I think that's really it. I mean, I think we talked about the last one. Obviously you need to have a specialty inspection. You need to check all these parts on the process. And in reality, there is, I mean, obviously everything is coordination and regular timely communication, right? I mean, if you know that you can have excess grout and things like that, just communicate a lot between the construction and the design, and start coming with the strategies of how to minimize. So yeah, I think, I mean, this part of the presentation is just some papers, but I think we talk about all these on the previous ones. We talk about drill shafts, we talk about the stabilization, and then obviously we have our previous recordings in YouTube and all these topics. And I think
wait, I want to see that one again.
This one?
Yeah, what is this?
This is just, it's basically all the stuff that is on YouTube. I don't know. I mean, I think during COVID, I think you are at the bottom, right? If you look the bottom on the second column, that is the That is the link to like the first one that we recorded.
Oh yeah,
Together
that was before I
long
bought
time
this
ago.
camera.
Yes. So yeah. So no, I mean it's. Yeah, I mean, I love doing these videos, right? And I love having these conversations on, with different people and talking about topics. And I honestly believe YouTube is a great resource to learn more about geotech, right? And like YouTube is not just to see videos of cats, right? And things like that. It has a lot of educational content. I play chess. I love chess, and I learn a lot of chess just by looking YouTube videos. And the same way, I like to kind of always,
You need to
promote
play.
people.
You need to play a game with me.
You play chess too?
Yeah.
All right. We'll play. We'll play. Next time that we are in Toronto or somewhere that we can meet, we'll play.
We
We'll
can
play.
play online, but we
Yeah.
should record the game so that you will not run away from the result. Yeah.
Yes, exactly. I don't know, man. You're intimidating me right there. So yes, I always say I love the game more than the game loves me. So yes, so it's good. But yeah, but that was really it. And then I always have to finish with this picture with my
This
companion
this
of
guy
adventures.
this guy will certainly be a geotechnical engineer. There's no other way.
We'll
He,
see.
yeah.
We'll see. We'll
You're
see.
you're you're making him love this business
I
and
hope.
this
I hope. I mean,
profession.
I grew up. I was presented to the industry when I was young. My grandfather was a civil engineer. My dad is a civil engineer. So when I was growing up, I always look our profession as a very respected and prestigious profession, and I think I always like to transmit that, even if he doesn't end up being an engineer, like that he understands the passion that I have for what I do and how much love like we have into what we do, right? And then he can apply that on whatever he wants to do in life. But I do believe that what we do makes a big difference in our world, in our society, and it's a beautiful profession. And geotechnical engineering, as part of civil engineering, is not new, right? I mean, we were talking about Tersagi and all that before the recording, and I do believe that it's recent and it's exciting. It's an exciting field, and I think we need to bring more people into our field. So I'm always happy to be an ambassador for our profession and try to recruit more and more and more and more. So yes, so
We
I'm gonna.
appreciate that. Thank you very much, Sebastian.
No problem,
Um,
no problem.
you were great as usual. The information is tremendously beneficial, and
Thank you.
we would like to see you again very soon.
Yes, absolutely. We keep recording. We
Although
have.
it's Christmas time and we have lots of obligations, maybe.
Mhm.
But if you have any time, just give me a call, okay?
Absolutely. I always love our conversations and the way that we take these subjects and break it into pieces and compare experiences.
Let's
And
have something now about ground anchors. Maybe
yes,
strand anchors, and
yes,
even reinforcement anchors, rebar
yes.
anchors.
No, absolutely. Let's do
Let,
that. Let's do that the next one. I do have one about, basically a state of the art on passive anchors
yeah.
and active anchors.
Hopefully, we can
And
cover at least some beautiful practical problems that
yes, no, absolutely. I
everyday
like that.
life of a geotechnical engineer.
I'll take you on that. I'll let you know when the time is there, and then we'll do another recording like this. So that's great.
Thank you so much, and thanks for everybody watching us. And we hope you subscribe and continue watching, supporting us and supporting our goals. Everybody, have a good weekend and enjoy. Thank you.
All right. Bye.
See you again, Sebastian.